but so that we can talk about velocity, which is the rate and the direction of motion, not just the rate, we need to describe what a scalar quantity is and what a vector quantity is. So something that is scalar is something that describes magnitude but not the direction. So everything we've done up until now in this physics unit has been with scalar quantities. We have not indicated a direction at all in any of the questions or in any of the calculations. So a good example of a scalar quantity is distance. Distance is the length of a path between 2 points or locations. So it's where the object or where the person went. We'll just pause for a second. All right. So until now, we've been talking about distance. And I'd like to make a little note that distance is just represented with a d. That's what it was in the formula. We know that time is represented with a t, speed with a v. Now when we talk about vector quantities, which is what we're going to talk about for the next couple of sections, a vector quantity describes the magnitude and the direction. So that means we're going to have an actual number plus we're going to have a direction. So that we can tell the difference between something that is a vector quantity and something that is scalar, the symbols for vectors are written with arrows above them. So some things that would count as a vector quantity would be position, velocity, acceleration, or displacement. Notice that a couple of the symbols repeat themselves. D is used for distance, and it's also used for displacement. So that we can tell the difference, displacement has an arrow over top of it. Yes, Ryan? That's a D, yep. Lowercase d with an arrow over top of it. The same thing goes for speed and velocity. Speed is a V, and so is velocity, but velocity has an arrow over top of it. So you'll notice on your formula sheet that you have two formulas that look basically identical. One of them is for speed and the other one is for velocity. And the only thing that's different is that the one for speed doesn't have arrows and the one for velocity does. Now you'll notice that there are a couple of things that don't appear on both lists. For example, time. Time will always be scalar. We will not associate a direction like north or south with time. Time doesn't have a direction associated with it. So even though you might use time to calculate velocity, time will not have an arrow over it ever. A couple of other values are only in the other list. We'll only really mention position when we're talking about velocity or displacement. Position is a term you'll see below used to describe where we are right now, not necessarily how far we have gone through our whole path. Now, acceleration can be scalar sometimes, but it's usually not. And so that's why I didn't put it on the list of things that are typically scalar quantities. Most of the time, when we talk about acceleration, we'll talk about a number, a value, and a direction. So the first thing you need to recognize is that scalar has no direction, vector has a direction. And some of the values that we use in our calculations are scalar, while other ones are vectors. Vectors have an arrow. Would anybody like to ask any questions about what the difference between scalar or vector is? So the first thing I'd like to talk about is the idea of displacement, because lots of people confuse distance and displacement because on the surface it seems like you're talking about the same thing. The first thing you need to recognize is that displacement is a vector quantity by definition. It describes the straight line distance, and I'm going to highlight that because sometimes distance and displacement are the same, but sometimes they are not. The reason that they wouldn't be is the idea of straight line. The other thing that displacement includes is the direction, which way we were going. If we wanted to talk math, which some of you indicated to me you wished we wouldn't, what it is mathematically is the difference between two positions. And you might say to yourself, well, isn't that the same thing distance is? And what I'm saying is on the surface, it kind of sounds like it's the same. So I'd like to show you an example that illustrates how distance and displacement are different. So on the bottom here, I have a couple of pictures, and I'll talk about the one on the left first. The one on the left is trying to illustrate to you how distance and displacement could end up being different. So I'm going to imagine in this picture that this is the starting point. Here's me. I have long hair, so that's what I'll draw. And I'm starting at my house, and I am going to jog to Starbucks, because that way I can drink a Starbucks and not feel bad about it. And to jog there, I'm going to follow the path that goes through Cimarron. That path does definitely not go on a straight line. So the blue line here that goes around in a curve, you'll see says that's the path taken. That represents where I actually went. So I followed the path, it turned left and right, I made a loop, I came back the way that I came, but I followed the path through the park, not in a straight line. And if I wanted to know my distance, I would literally measure how many meters I actually moved. And so let's say, for fun, that the path I took was 2 kilometers. Now that's how I got there, but is that the most direct way I could have gotten to Starbucks here at the end? There's Starbucks. And the answer is no. If I could have walked through people's houses and made a perfect straight line, I could have gotten there in much less distance. So displacement in this case would be where I compared my initial point and my final point and how far they were away from each other if I drew a direct straight line. So displacement here is a straight line. It's direct. There's no turning, no bending, no winding around. It's the shortest distance that I could make between those 2 points. And let's say, for fun, that that's 800 meters. I would also have to indicate which direction, because that's one of the things that displacement involves. So if I follow what the picture looks like, I'm going kind of down and towards the right. So I'm going to say that I was going southeast, and that is how I arrived there. Now, is 800 meters southeast where I actually walked? No, that is if I directly went from the initial point to the final point. So the thing I want you to notice first of all is that distance and displacement are not always the same. Sometimes they could be, but most of the time they're not. Most of the time, one of them is bigger than the other. And if you think about it, it would really make sense that distance should generally be the one that's bigger if there's going to be a difference. Now, the other thing I'd like to show you is how one of them could be 0 while the other one is not. So my example on the right that has a number line is where I'd like to illustrate to you that displacement can be 0 when distance is not 0. So I'm going to show you how someone could move, and move a lot, but have their displacement actually be 0. So I'm going to use someone as an example. Who's going to be my example? Who takes the bus? Yes, Carter, you're going to be my example. You take the bus. Here's Carter. He's at his bus stop. The bus is late. He's annoyed, so he's pacing back and forth at his bus stop, singing. What will he be singing? So I'm sorry, what's that? He'll be singing what? What's his favorite? Wolves? I don't even know what that is. How about let's say he's singing the song from Frozen. That would be funnier, I think. Yeah. So here he is. He's singing, la la la, and he's waiting for his bus to show up. And while he does this, he's walking back and forth. So let's say, first of all, he goes 7 meters to the right, and then he walks back this way, and he walks 16 meters to the left. Then he walks 4 meters this way, and then he comes back 4 meters that way, and then he walks 9 meters, and he ends up right back where he started. Now, if I look at this question and I ask myself, what's the displacement? Displacement is always, where am I compared to my initial point? On this line, this is the initial and the final point. That's where he was when he started. That's where he was when the bus finally showed up and he stopped pacing. So in this example, displacement is 0. He is exactly where he started, but distance is not. In this particular example, if I wanted to figure out distance, I would add up all of the meters that he traveled. Exactly. If you end up where you started, no matter which way, whether it's a circle or a straight line, if you end up where you started, your displacement will be 0. So I would add up 7 plus 16 plus 4 plus 4 plus 9. So that gives me 24, 33, 40. 40 meters. So he moved. There was a distance, but displacement is 0. Now, some people prefer some sort of math way to figure out what displacement actually is. So what I'm going to show you guys, and this is what will come next, is when we're thinking about direction, we'll consider some of the directions positive and some of them negative. So most of the time, we'll consider going to the right, positive, and to the left, negative. So that's positive, that's negative, that's positive. The reason that we'll do that is so that we could add these numbers up and find displacement. So you can figure out displacement by adding up the values, but you have to include the direction. Which way were they going? This means that I'll go plus 7 minus 16 plus 4 minus 4 plus 9. When I do that, I end up with 0 as my answer. So in this example, displacement is 0, but distance is 40 meters. Would anyone like to ask any questions about either of those examples where we compare distance and displacement? So then we'll talk about directions next so that we know the way that we would identify which way something is going. So we'll usually use what's called the navigator method. In the navigator method, we'll be talking about north, south, east, and west. So what I need you to know is that 0 degrees means north, 90 degrees means east, 180 degrees means south, and 270 degrees means west. If you notice, I've added 90 each time. Now you'll notice that on a real actual compass, there are lots of directions in between north, south, east, and west. I don't need you to be super specific about those. Maybe one day you'll learn the difference between west-northwest and north-northwest. But what I want you to recognize is that if the number is not exactly 0, 90, 180, or 270, that it'll be an intermediate direction. So for example, if I said that a ball is rolling at a velocity of 2 meters per second, that's the magnitude or the rate, and then in square brackets, 135 degrees. The square brackets are always what we use for direction. So if you see something in square brackets after a speed measurement, you know that that's the direction that the person was going. So in this case, since we said 135 degrees, which way is that actually? Well, since 135 is right here, it's in between east and south, we would say that the person is going like that. They're not going exactly east, they're not going exactly south, they're going somewhere in between that. Now it's possible that instead of using north and south and east and west, we could use something a little simpler. So in addition to north, south, east, and west, we could also use up, down, left, and right. That would be pretty typical. We could also, just on sort of the horizontal axis, talk about something going forwards or backwards or in reverse. So those are all descriptions that could be possible for the direction that something that is a vector is going. Regardless of the word or the symbol we actually use, you've basically got 4 ways that something can go, and you'll put it in a square bracket after your answer. Does anyone want to ask any questions about directions or the numbers that go with them? So then we'll move on to the formula. You'll notice if you look at the velocity formula that it looks the same as the speed formula, except for 2 little things. In the speed formula, there was no arrow over the V and no arrow over the D. Other than that, it looks exactly the same, which means that it works basically the same way. Velocity should be measured typically in meters per second with a direction. So I put those square brackets there to remind you have to put a direction. Displacement should be measured in meters with a direction, and time is typically measured in seconds without a direction because time is not a vector. And so the way we know the difference is whether or not there is an arrow. Vector quantities always have the arrow. So I'll show you an example question where you would use this formula. In the example, and this would be typical of most examples where we're calculating velocity, the first thing you're probably going to have to do is to figure out the displacement. So in questions where we were talking just about distance, usually we just told you what the distance was, or it was an easy little calculation, final minus initial. For displacement, you really have to recognize the direction to know if you should add the values together or if you should subtract them. So when I look at this question, it says that a student walks 10.0 meters east. We're going to call east a positive direction because it's the one that goes to the right. He does that in 7.00 seconds, then he walks another 12.0 meters to the east again. That means that in this case, both of those numbers are positive. I'll add them up. If the student had walked back towards the west, I would have subtracted that. And so when we're figuring out displacement, there's not one easy little formula that you can use to figure out displacement because you have to consider the direction. If you'd like a formula, what you really need to do is final minus initial position. But to know the final and initial position, you kind of have to do the other math first. So some people like to draw this, some people like to just use math. If you think about this, the person went to the east 10 meters and then went another 12.0 meters east. So if this was their initial point, this is their final point. Oh, that was interesting. Huh. Can I still do this? Okay. So when you're figuring out displacement, you have to consider their final and initial position. And to know that, you have to think about which direction they were going. In this person's case, since both of them were east, I'm going to do 10 plus 12. This means that displacement was 22.0 meters east. Now I had to put 0.0 because both of my original values had a decimal place. When I add and subtract numbers, and that's all I did there was added them up, I have to keep the same number of decimal places. I also had to indicate the direction, and since the question said he was going east, east is the direction. Now average velocity will be calculated just like we calculated average speed, except I use displacement, which has a direction, instead of distance, which doesn't. So I'll do 22.0 meters east divided by 7.00 seconds. And the answer that I get is 1.466666, etc. Now I know that I need to round that answer off. Since I was multiplying and dividing here, not adding and subtracting, I'm not looking at decimal places anymore. I'm looking at significant digits. Since these both have 3 significant digits, this has 3 significant digits, that's how many I'm allowed to report in my answer. So I'll round this to 1.47. Now my unit, since I was dividing meters by seconds, should be in meters per second. And I have to put a direction, so I put E in brackets to say that I was going east. Would anybody like to ask any questions about this example here? One thing that you'll notice is since you have to put a direction in your answer, questions about vectors will have an additional point given to them because the direction has to show up in your answer as well. So usually I make things out of 3. A lot of the time, vector questions are out of 4. So what I'd like to do then is show you 2 other examples to remind you that you would have to manipulate this formula just like you did with the speed formula. So this will give you some good practice for tomorrow, to calculate displacement or to calculate time. Yes? This is not on the quest. The speed formula is, but this specific formula is not. So there's 2 questions here. One question asks you to figure out the displacement of the boat. The other question asks how long will the plane be in flight, so we're looking for time. So I'm going to pause here to give you guys a chance to calculate these, and I'll write the answers on the board in just a few minutes. So the 2 questions have the solutions on the board, and I just want to point out a couple of things about them. the first thing I want to point out is that on your formula sheet, there is a formula just for displacement. And a few people asked me, should I use that? So the final minus initial idea. You could if you knew what the final and the initial displacement of the object was, but you don't in this question. And so there's two ways that you can find displacement. Either from me telling you the position of the object, or because you calculate it using the velocity formula. And so one of the things I notice when we get to like the end of this section and we're talking about distance and displacement and a bunch of other things all at once, is that people rely too much on their formula sheet to tell them what to do. And so I'm just pointing out to you, you can get displacement two ways: by subtracting final and initial point, or by calculating it with this formula. Now I'm just going to point out a couple of things here. How did I know that north went in my answer? Well, that's the way the object was going. So always look to the question to figure out the direction that your object was moving, or that the person was moving. Don't forget about significant digits. There are 3 significant digits in both of those. So I put 3 significant digits in my answer. Now, a few people asked me, do I need to use scientific notation? It wouldn't be wrong if you did, but you don't have to. Scientific notation is necessary when your number is too big or too small, and you can't make the correct number of significant digits easily. Since I needed 3 significant digits and my answer was 112, I don't have to do anything. That is 3 significant digits. Just so that you know, if I were to put this in scientific notation, it would be 1.12 times 10 to the power of 2 meters north. Both of those would be equivalent to me unless I specifically asked you for one type of answer. Does anyone have anything they'd like to ask about number 1? So then for number 2, we're talking about time. Now remember, time is not a vector quantity, so time will not have a direction on it. And the other way I know this is by looking at the calculation I was doing. To figure out time, I take distance and I divide it by velocity. And if I look at the units, I have kilometers on the top and kilometers on the bottom. They cancel each other out. I have west on the top and west on the bottom. So even though west isn't technically a unit, it's there in both spots. So it would make sense that it gets canceled out for my final calculation. The only thing that's left is hours. That's how I knew it was my unit. This question also has 3 significant digits in it because both of my original values had 3 significant digits. Now the other thing I wanted to mention, because I did this here, notice how I circled my answer. I used a different color pen. You don't necessarily have to do that. But please, when you are doing a calculation, I need to see which thing your final answer is. Some people have the habit of writing more than one thing down and hoping that one of them is right. And while that is tricksy of you, and I applaud your efforts, I need to know which one you think the answer actually is so that I can judge whether or not you know about significant digits and about formula manipulation. Does anyone want to ask anything at all about number 2 or anything that's on the screen here? You just want to what? All right. The next thing that we need to discuss then are position time graphs. So the first thing I'd like to say is that a position time graph is a lot like a distance time graph in that things are set up the same way. Time, you'll notice, is always on the x-axis, and that's true for all of the graphs that we're going to make. Time will be on the x-axis. What is on the y-axis? That's where position goes. So it's kind of like I've replaced distance with position. Otherwise, my graph is going to look pretty similar. The thing that you'll notice is that position has to have a direction associated with it, whereas distance did not. So in this particular example, since I put an E in brackets, I'm saying that the direction was east. Now I could ask you the same thing about a position time graph that I could ask you about a distance time graph. I could ask you, what is the average velocity? And the way you'll do that is by telling me the slope. So on your quest tomorrow, I will ask you to find the speed of an object by finding the slope of a graph. You'll be doing the same thing as you're doing here, except on our quest tomorrow, there's no directions. So the only thing we're really changing here is that there's a direction involved. So if I'd like to figure out slope, it's always the change in y over the change in x. On this particular graph, since the y-axis is position, I'm going to do final minus initial position over final minus initial time. So I'm doing the same thing, but instead of distance, I have position. Class over for you right now? Oh, okay. So I'm going to pick 2 points. And for fun, I'm not going to pick the first and the last. I'm going to pick these 2 points. So when I pick 2 points on the line, and it's key that they are on the line, the first one, which is the one that's closest to the left, will be your initial point. The second point, which is the one that's farther to the right, will be your final point. So I'm going to do final minus initial position. So if I follow this over, my final position is 40, my initial position is 30, and I was going east, so that's my direction. If I think about my times now, my final time was 4, my initial time was 3, and there's no direction associated with time. Now remember that when you do slope especially, you have to do the subtracting on the top and on the bottom as though there were brackets there. So you do that first, then you do the dividing. This tells me that I'm going to divide 10 meters east by 1 second. That tells me that my answer is going to be 10 meters per second east. Now, based on the numbers I see on that graph, I should only have 1 significant digit in my answer. So I will need scientific notation here. To do scientific notation, I take the decimal and I move it so there's only 1 number in front of it. So I'd be moving it 1 spot. And I'm simply going to say 1 times 10 to the power of 1 meters per second east. So I got rid of the second digit so that I only had 1 significant digit in my answer. Now so far, that really doesn't seem any different. The only thing that we've really changed is that we've added a direction. Now a position time graph could look like that, just a line that goes in one direction. But when we're talking about position time, very often we'll see something a little bit different. And so I'm going to show you a different kind of graph. So notice when I set up this graph, I on purpose didn't make an L shape. I kind of made a T shape. This spot right here will be 0. And on this graph, let's talk about north and south. On a position time graph, I could have 2 directions. So I don't have to just be going one way. Because direction is included now, I could represent both of them. So on this graph, I could go towards the north or I could go towards the south. The 0 will be my reference point for where we start going north or start going south. Let's just imagine a couple of lines. Let's put a 5 and a 10 and a 5, and a 10. Now I'll still have position in meters as my axis label. I'll still have time in seconds as my x-axis label. But what I'll notice is that my graph could have more than one line on it. So my graph could, for example, look like this. It could go up, it could go down, it could even cross over the 0 line. And so I'm going to talk about what I would refer to as the 3 sections of this graph. Let's just say for fun that that's 5 seconds, just so we have a number to use. In the first section of the graph, where the line is going up, so this portion here, I can see that the slope goes from the bottom towards the top. Here, the slope would be positive. At 5 seconds, the line changes direction. Now, since slope has to be based on one straight line of best fit, what I actually have at this point is a new slope. So if I was going to calculate the slope of this graph, I would have to do it in 2 sections because there are 2 lines. Starting here, now the slope would be negative because I'm going down. And so the answer for slope can be a positive number, but it can also be a negative number. Now at the point where I change from positive to negative slope, what I'd like for you to recognize, because it's a misconception, I'm not slowing down here. That is not what is happening. When my slope changes from positive to negative, what's actually happened is a change in direction. So it does not mean that I'm going faster or slower. It means I'm going the other way. So if, for example, I calculate the slope of the first section, so we'll call that slope 1. In the first section, I go from 0 to 10 meters north in 5 seconds. So I know that slope is the change in position over the change in time. So 10 meters north, 5 seconds. My answer is 2 meters per second north. Now if I look at the second section of the graph, and we're going to assume that right here is 10 seconds, what you'll see is that my slope has the same numeric value. For slope 2, I'm going to think about this point and this point because they're both on the line. For slope 2, I can't just take the big number minus the small one. My point closest to the left always has to be initial. My point closest to the right always has to be final. So if I think about the change in position over the change in time, I'm going to go 0 minus 10 meters north over 10 minus 5 seconds. Now, if we do this calculation, what you end up with is negative 2 meters per second north. And so you'll say to me, no, see, you're dumb. That is less. That's slower than it was before. You're a bad teacher. And I'll say, haha, that's not what the negative means. The negative is just telling me which way I'm going. It's not telling me how fast or slow. That's what the 2 is doing. The 2 is telling me how many meters per second. The negative is just telling me I'm going the other way. So I could write negative 2 meters per second north, or I could write positive 2 meters per second south, and I would be saying the same thing. So what I'm trying to illustrate to you is that if the slope starts going down on a position time graph, it doesn't mean that we're going slower. It means that we're going the other way. Would anybody like to ask any questions about this idea of changing direction?